forget that tomorrow is the laptop day. We will be doing something on College Board. I'll tell you more about it tomorrow. Don't worry about it right now. But bottom line is you'll get points for doing it, and it's going to basically, it's a review of 1-1 to 1-6, and it will give me an idea, you an idea, and the county and the school administrators how individually you guys are doing with the material. So some students might blow it off and Christmas tree it. It's not going to make you look really good. Doesn't hurt me. I mean, maybe it makes me look bad, but it doesn't mean anything. But it would be like, ooh, this student is really not where they need to be, okay? So just, that's what tomorrow is, but you're not getting a grade for it. But you'll get credit. All right, but I'll tell you more tomorrow. All right, so there's only one day of lesson 6. That's why I didn't put day 1 or day 2. So we're going to do 1.6 today. And then tomorrow's the computer, and then we have 3 sections left before our next test, and then we're done with Unit 1. So 1.7, 1.8, 1.9. And they're longer, so some of them take 3 days, some even take 4 days. So just know, this one takes only 1 day, so there we are. I had thought this was going to be really easy for my other classes, and for some people it was. I think it depends on who you had last year, honestly. But some people had some questions about this. So it's only, first period was able to finish the assignment in class. I don't know if they really understood it. I think they did, because second period threw me off. They kind of seemed a little confused. So you guys seem to do really well on these things. So let's see how you guys do. All right, so what we're doing is talking about basically 2 things today. End behavior and multiplicity again, okay? So end behavior has to do with what's happening on the ends of the graph. And you might remember hearing that in Algebra 2 before, okay? And so we're going to do something called the leading coefficient test. And to find out what happens at the end of a polynomial, which I'll break down even more in a second, we look at 2 things. We look at the degree and the leading coefficient, okay? So what we're going to be determining is what is happening at the arrows at the ends of graphs, or predicting what the arrows would be looking at a polynomial. And we do it using the degree and the leading coefficient. And if you remember, degree is represented by the lowercase n, degree, and then leading coefficient is a sub n. And degree can be one of 2 things. A degree can either be even or odd, okay? And a leading coefficient can either be positive or negative. Those little pieces of information will tell us if the graph goes up forever in both directions, or one goes in one and one goes the other, and we'll talk about that down here. But before we get to that, I have to introduce something called limit notation to you. This is brand new, I think. I don't think you've done it before. We'll be using it a lot in here, and if you choose to go on to any higher maths, it's the gospel of how you note a lot of things that happen with graphs. And it's like, I talk about math being a language that you've learned. I mean, think back to elementary school. I don't know, like the first grade, you learned this symbol right here. Like, your teacher taught you that means you take the numbers on either side and you combine them and you get a total, right? You read it as plus. You know that symbol means plus, right? It all started with that symbol. And then you learn subtraction and multiplication and division, and what's the long division symbol, and remainder, r, and x to the second power, we call it x squared, and we got into letters in our math, and all the different symbols and ways we read and say math. You've been doing it, you don't even know you're doing it anymore, okay? This is just another part of the language that you're going to learn. So limit notation. So limit means how far something's going or where it stops, okay? And notation just is a way of writing it, okay? So let me show you. We start out by writing L-I-M, and it's usually written like that, like a cursive L. Don't worry about knowing cursive or not. You could make a capital L, but I'm going to write it the way you would see me write it, how you would see it in a book, and so on. So the limit of f of x. What does f of x mean? Y. Yep. Limit of f of x as x, this arrow symbol means approaches. You actually say the word approaches. The limit of f of x as x approaches something. There'll be something right there. For us today, and for a while I think, it's infinity or negative infinity, you'll see what I mean in a minute, equals whatever the answer is. So let me just break this down to you in a different way. What this is saying is what is happening to the y values as the x values go to the left or to the right. So it's basically saying as x's get bigger or smaller, so if x's approach infinity or infinity, what are the y values doing? Are they going up? That's infinity. Going down? Negative infinity. And we'll see that in a second. So just hold that thought. Let me just talk about end behavior separately from that first, okay? Using these 4 graphs. So just hold on the limit notation. So here's 4 graphs. This is all 4 possibilities of end behavior, okay? So under coefficient, I want you to add degree on all of these, because it's really 2 things that determine end behavior. Degree and the sign of the coefficient. So the top 2, I want to start with just what the degree is. Remember I said degree is either even or odd. So think about even numbers, 2, 4, 6, 8. We really just do 2 or 4 in most math. And then odd would be 1, like a line. 3 is a cubic, and you can go further. So degree, look at the end behaviors. What this is saying is, what are the arrows doing? That's what end behavior means. Ends of the graph. What is the behavior? Where are they heading? Even though we don't see it, we should be able to say what's happening there. What's the behavior? So anytime they go in opposite directions, our degree is an odd number, okay? And so you think opposite and odd together, okay? So this one is going down on the left and up on the right. This one's going up on the left and down on the right. How can we memorize that? And how do we know which one is which? Well, how do we know which one is which? Is what is the sign of the coefficient? So let's talk about this one's positive, this one's negative, and I'm going to tell you why. I want you guys to think of the most famous odd degreed graph. What's one that we have graphed since we were 11? A line, right? Lines. Think about lines. You know a whole bunch about lines, right? A line is x to the first power. That's odd. We know a lot about lines. We know that a line that rises from left to right has a slope of what? Positive or negative? Positive, right? That's a positive slope of a line. It rises from left to right. Look at its end behavior. It's down on the left, up on the right. Same as any odd numbered graph. It doesn't matter what happens in between. See how it's dotted? What matters is what happens at the ends. And you can kind of picture a line going right through there, where it's going down on the left and up on the right. So anytime we have, and then let's do over here, if a line goes like this, you all know it has a negative slope. And by the way, slope is just your leading coefficient, right? We call it m, but it's the number that comes and it hangs out with the degree exponent. So m is your leading coefficient. So positive slope rises left to right, negative slope falls left to right, and you can see it right there. So up on the left, down on the right. And you probably in Algebra 2, I know for sure in Ms. Shackton's class that you guys did end behavior. Sometimes we do arrows. I don't really know how she did it last year, but I know she covered it. So like in my Algebra 2 class, we just kind of do this. We say, oh, it's on the left, it's going down, on the right, it's going up. On the left, it's going up, on the right, it's going down. And we always write left to right, just like we read a graph, okay? But we're going to do it using limit notation now. So here's the thing. This is really important, okay? Let me just make a basic graph, right, where the origin is in the middle. So if we were pointing to the right, if I'm saying let's go to the right, that's our x values are going towards what? Where are the x values going towards this way? Infinity, right? X values are going towards infinity if we're going to the right, okay? X values to the left are going towards negative infinity, right? To the right is positive infinity for x's, to the left is negative infinity. You guys already know that. Think of domain and range. And then on the y-axis, what's happening if we go up? What do we call that? Infinity, right? Positive infinity, that's going up. And y is going down, our negative infinity. that's something you already know. It's basically just putting it together in this weird new language. So let's look at these two limit notations here. They're really small. What this says is the limit of f of x as x approaches infinity. That's a positive infinity symbol right there. So what it's saying is, where are the y's going when the x's go to the right? My y's are going up, right? Right here. As my x's get bigger, my y's also get bigger. We're going up towards positive infinity. This guy, as x approaches negative infinity, that negative is really small, sorry guys. As x approaches negative infinity, and that's hard to see because it's going down, but remember, as it goes down, it's also going to the left, right? It's going like this. So as x's go towards negative infinity to the left, what are the y's also doing? Going towards negative infinity. Okay, look at this one. As x approaches negative infinity. So as x goes to the left, what are my y values doing? They're going up, right? As I go to the left, my y's are going up. So that's positive infinity. If we're going up, it's positive. Look here. As x approaches positive infinity, that means goes to the right. As x is going to the right, which it is, what are the y values doing? Going down, right? So, negative infinity. Squeeze it in there. Down is negative infinity. All right? Stay with me. These degrees are even. You probably figured that out. Even degrees have same end behavior. Up, up, down, down. How do you know the difference? Well, I gotta tell you. Up, up is positive, down, down is negative. And think of the most famous even-numbered graph that we work with, known as the parabola, x squared, right? X to the second power. You guys have seen this before. I mean, I haven't really gone into quadratics with you. We've touched on them, but if you have a positive quadratic, positive number in front, these positive people smile, it goes up, up. So anytime you have to decide, if they're going up, up, you think of a positive parabola. Oh yeah, it's positive in front. And then here would be a negative, people frown, right? You can see them in there. Remember, we don't care what happens there. It's all about the ends. Negative people frown, so it's down, down. Okay? So if you know about lines and parabolas, you know all end behaviors in the entire world. Okay? You know all of them. Because if you just think back to any odd number, compare it to lines, any even number power, compare it to parabolas, you know how to answer the question. All right, let's finish this real quick and then we'll do some examples. Up, up, as x approaches negative infinity. It's going to the left. It's slight, guys, but it's going to the left. It's also going up, positive infinity. As x goes to the right, y goes up. So as x gets bigger, y gets bigger. As x gets smaller, y gets bigger. And then the opposite here. Both of these are going down, so they both should have a negative in front. Right? It takes some getting used to. There will come a moment usually where you're like, students will be like, oh, I totally see it now. It takes a little practice, okay? Don't worry, we will practice. All right? Stay with me, stay with me. Go to example 1. So we looked at some graphs. Let's kind of put it all together. These are polynomials in standard form. Exponents are in descending order, okay? The n, remember, is your degree. So our n would be 3, right? And we know that that is an odd number. A sub n, that's our leading coefficient. What would our leading coefficient be? -1, which is negative. Degree. Okay, so what I think in my head, because, well, I'll get to that. What I think in my head is a line, right, with a negative slope. So I'm like seeing this in my brain. I'm picturing it, right? Odd is a line negative falls left to right. So let's fill in this behavior. As x goes to the left, what are the y's doing? Increasing, going up, positive infinity. And it's really hard to see the negative there, but look at the difference in what the negative infinity looks like and the positive. So that means left, this means right. What? It is? It doesn't? Huh. You guys are the first ones to tell me. I taught this twice. Thanks. I don't know. She probably changed it later after I already printed yours, and so I apologize. Don't know. Whatever. We had an AP meet. I'm being recorded, so I'm being careful. We had an AP meeting yesterday. It was a little frustrating. Okay, so as we go to the left, we're going up. As we go to the right, we're going down. So you'll have a chance to do that in the homework if you don't have time to write that right now. I want to remind you that the turning points, we learned this already. Does anybody know how many turning points we're going to have in this one? 2. That's your degree minus 1. We learned it before. So just with this information, we can sketch a graph, okay? It doesn't have to be, actually, that's not where we are. I could put this in my graphing calculator. Don't take the time to do it. I know you guys know how to do it. You could type this in your graphing calculator, hit graph, and you would see this. So I'm going to graph it for us. This is what I would see. This is a sketch. It's not perfect. But I want you guys to see there's 2 turning points. And there's that end behavior that matches a line with a negative slope. You don't care about what happens in between. End behavior literally means what direction the arrows are pointing. That's it. That's all it's telling us. Okay? Look at this one. We have a degree. Dylan, what's the degree here? What's the n on this one?
4.
Yes. And what would a sub n be, guys? Yeah. So 4 is even, 1 is positive. That's what you're looking for. Okay? So I hear even, I go parabola, positive people smile. I know my graph is going to be up, up. I don't know what else is going on. Some craziness. Who cares? That's all that this is asking. So you can just follow along with me. I don't want you to waste too much time. But as we go to the left, we go up. As we go to the right, we go up. Right? Up, up. Positive, positive. That's what that means. And I'll just tell you when you sketch this, number of turning points would be 3. Look at that end behavior, just like a parabola. 3 turning points, 1, 2, 3, okay? All right, very last example. Unless question? No? Last example, let me just tell you, and this is talking about multiplicity. Last thing. If a polynomial function has a factor that is repeated, that duplicates the roots. The x intercepts the solutions. We already know this. We call it multiplicity. Right? Multiplicity. Now, we've done before where you were given, we're going to do it again in a second, you're given something in factored form, or we had to factor it first, but this is factored form, thank you. And you set each of your factors equal to 0, you solve, and you state the multiplicity. And that's all we had to do. So like this would be x equals -2, right? Multiplicity of 3. This would be x equals 1, multiplicity of 2. And we'll write that in a second. And we were done. But that multiplicity actually tells us some really important information. It tells us how our graph interacts with the x-axis. Okay? So if you have an odd multiplicity, so you have 1 of something, 3 of something, 31 of something, the graph will cross the x-axis at that 0. And I'll show you what I mean. But cross goes right through it. Goes right through the x-axis. Okay? If the real 0 has even multiplicity, there's 2 of the same number, 4 of the same number, so on. There's a couple different ways you can say it. I think this book uses, or this author uses touch and turn. I've always said bounce. And I'll show you what those look like on this graph here in a second. Okay? So here's a graph of this factored form polynomial. Okay, here's a graph of a polynomial. Here's factored form of that polynomial. we could FOIL it all out, take 20 hours to do it, and get it in standard form like this. Okay, so they're all just different forms of polynomials. So let's identify our zeros in the multiplicity. Okay, so we just talked about it. If I set x plus 2 equal to 0 and solve it, I get -2, right? How many of them do I have? 3, right? 3 of the same thing. Which, of course, is odd. And odds are going to cross. Okay, we'll look at it in a second. X equals 1, right? Set x minus 1 equal to 0 and solve it. You don't have to show the work. We would get 1. And since there's a 2 up there, that's a multiplicity of 2. 2 is even. Okay, not the answer, not the 0. It's the multiplicity that we're looking at. 3 is odd, 2 is even. That, I'm just going to write bounce. But you could write touch and turn. Just know the difference. So they put this in the graphing calculator and put it here for us. So what we have now is we should have a 0 at -2. We do. See how it's crossing it? It crosses the x-axis. And we have a 0 x-intercept at 1. And this is an example of a bounce. It touches it and turns. Or you can think of it as a ball. It hits the ground and bounces and goes back up. Even multiplicity, odd multiplicity. But there's one more thing I have to tell you. This is a cross, right? It doesn't turn around. It keeps going through. But do you see how it has like a little curve to it? This is actually a change in concavity. When it looks like this versus a graph that goes like that kind of a cross, just goes straight through. This is a multiplicity of 1. This, when you see that the little curve there, means it's a multiplicity of 3 every time, okay? So it's crossing, but it's doing a fun little curvy cross, okay? Versus a line that's x to the first just goes right through the line. You never had a little curve there, just use graph or intercepts or whatever, okay? So for this class, we're only going to do multiplicities of 1, 2, and 3. So you're either going to cross like normal, which is this. That's a multiplicity of 1. And you'll see examples in the homework. Multiplicity of 1. You'll see a multiplicity of 2, which is a bounce, or a multiplicity of 3, which crosses, but it does a little fancy cross. Crosses a little fancy. Okay? So let's go find your 1.6 practice. There should only be one, because there's only one day of this. This is what takes me so long. This is new, but she gives us, I have to cross so much stuff out and fix mistakes and stuff like that. It's better than having no curriculum, but at least I have something, but there are some mistakes. So I apologize that you didn't have the limit notation there. Okay, so 1, 3, and 5 go together with that polynomial. 2, 4, 6 go with that. So I'm going to do 1, 3, and 5 with you, and then you'll know how to do those. And then you're only have 4 more problems on the next page. Okay? So let's look at this first example. Here's our polynomial, all right? And it says to identify the zeros and state the multiplicities. That's what we just did. Okay? So let me tell you this. You get solutions from your x's, just not in real life. Now, I'm being silly for a reason to help you remember. We are going to get zeros or x-intercepts from any factor that contains an x. So this guy is going to give us some factors, and this guy is going to give us some factors. When you come over here, we'll get, I meant zeros. We'll get zeros from that, zeros from that, zeros from that one, and that one. The negative in front doesn't have an x, so it doesn't give you a 0, just so you know. There's no x-intercept from a negative, okay? So when I set x squared equal to 0 and solve it, what do I get? 0. Square root of 0 is 0. But since it's a squared, we do have a multiplicity of 2. Okay? So if that was x to the 7th, we'd have 0 multiplicity of 7. Okay? And we have x equals -3 with a multiplicity of what? 1. So this one would bounce. Use an arrow. This one would cross. And we're going to sketch that graph in a minute. So, okay, so even numbers bounce, odd cross. And that's a straightforward, just go right through because it's 1. Yep. Where's the 3? It's still a cross, but concavity changes. It makes that little curvy thing. Let me stay with that question. Let me show you what it looks like. Look at these 3 graphs. You're going to have to do something with these in a minute. That's a cross, right? That's a cross, and that's a cross. If you look closely. So 1, 1, 1. Multiplicity of 1, multiplicity of 1, multiplicity of 1. This one's a cross, multiplicity of 1. This one's also a cross, but do you see how it changes the concavity? That's a cross, but it's a multiplicity of 3. Cross, bounce, cross, cross. Okay, do you guys see what I'm talking about there? That's the only ones we're going to do, so as long as you understood that. So there's 2 types of cross, just a regular old cross and a change in concavity cross. The bounces are really easy to see. They look like a little parabola. Okay. All right, back up here. Safety and behavior. We're going to use limit notation, okay? So let's do the limit. Get used to writing it and seeing it and hearing me say it so you can say it. The limit of f of x as x approaches, let's do the left first, negative infinity. To the left. As x goes to the left, also known as negative infinity, what would let's just set them both up. The limit of f of x as x approaches positive. Then we'll talk about it. Okay. Because we need to know what the first term is. Don't forget, all that matters for concavity is the first term. I can't find anything. Is the first term. That's all that matters, right? That's all you have to look at. But what do we do when it's not in standard form, but it's in factored form? I mean, what the answer is, you could distribute and get it in standard form, but that's too much work on some of these problems. Like a problem like this, that would take forever. If you only need the first term, you just take the first, the x part of every factor. In other words, x squared times x to the first. That's all we need. Think about it. If you did distribute, you would do that. That would be your first term, right? X squared times x to the first, which is x to the third. Okay, look at this one. Let's do this one together because I got a lot of questions today. Look at this one. So when you go to this one, we have x and we have x and we have x. If I put those 3 together, I get x to the third. But don't forget there's a negative in front. So if I did FOIL this out, like I said, it would take a really long time. This is like a -1 that you would multiply by everybody. So that -1 is part of the problem. It's -1 times this times this times this. So this would be negative x to the third. Okay. So you don't have to FOIL it, you don't have to make it be in standard form to know what the first term is, because that's all you need for end behavior. So if I'm looking at x to the third as my first term here, I think odd, line, positive slope. I'm actually picturing this in my head. Like I see that in my head. And so that means as I go to the left, I'm going down, right? So that's negative infinity. As I go to the right, I'm going up. That's positive infinity. Do we see that? That takes some getting used to. Okay? Sketch. Okay? Let's start with our zeros. We have 2 zeros. We have one here at 0 and one at -3. I know I start down, right? Start down. And at -3, I cross. Okay? So I'm going to start down and I cross. That's all I know at the moment. I don't know where I'm going. Well, I know something's going to happen, but I have to get back to this one. So I'm going to have to turn around somewhere. Pick a turnaround point. We don't care about it right now. We're sketching around. So turn around so we can come back to our next 0. And what are we going to do at this 0? Bounce. So we touch it and turn and we go off to positive infinity forever. So that's a good sketch. This is a guess, okay? We don't know what this point is. We don't know. We just turned around because we knew we had to come back and hit this next zero. So that's a sketch of the graph. Yeah. Sure. Yes, because it just depends on what's coming next. So if I have, let's say I'm starting down and I have a bounce here, then I'm definitely, yeah. So wherever my next zero is, it could be here, it could be here, I would have a turnaround point when I have to hit it. But yeah, you could bounce below the axis. But if you just understand the end behavior and where your zeros are and crossing or bouncing, it kind of leads you. You know what I mean? And it's a sketch, so it doesn't have to be perfect. But yeah, you could totally have a cross there. You could have a bounce here. I mean, it could do all kinds of things. Yeah. Okay, so I'm going to put the key up so you guys can work on 2, 4, and 6 the same way we just did. And then you just have a few questions in the back.